So when you have like a young solar system, so imagine like our solar system,
but
like you're talking like billions of years ago.
But our solar system was originally a cloud of dust that coagulated.
Yeah, so basically what happens is you have like imagine a big cloud of like gas and dust, and it collapses on itself. And at the center, you're going to start having like a young star. So fusion hasn't yet started because the mass isn't big enough. But you still have like this core, and you still have a bunch of gas and dust that's orbiting around.
Yeah.
So imagine like a record player. Okay, so at the center of the record player is this young star, and around the record itself is this thin layer of like gas and dust. And in that kind of system, some of the gas and dust is going to fall onto the star, and the star is going to grow, and then it's going to be like a full-fledged star.
So Jupiter would be like a failed protostar. Or around the same size. At one point, Sol was probably that size. This is what I've heard before. It just didn't have enough mass in order to conduct enough nuclear fusion to become a star.
That is the current theory.
Yeah.
But forget about like a binary system.
Yeah.
There's two stars. Just imagine like a single star forming.
Okay.
Okay. And then in that accretion disk, so in that thin like record of gas and dust, you're going to form planets.
Okay.
Okay. And so you basically have like 10 million years.
Yeah.
Okay, to form a planet. Because within those 10 million years, all the dust that can be used as planetary material is going to fall onto the star.
Onto the star, so you can't use it for Earth or Jupiter or whatever.
You basically have like 10 million years to grow from like little dust-sized particles that have to like clump together and then collapse via gravity, to form individual planets. And so basically we're studying this kind of like young system. So what is the star part doing? I wasn't so interested in the planet formation, but I was more interested in what the star does.
The angular momentum of that dust cloud is conserved in the star. That's why all of our planets, except for Uranus, is rotating in the same direction that probably that dust cloud was also rotating it.
Yeah, that's right. So when the planets form, the gas and dust is all orbiting the same direction.
Yeah.
And so if the planets form, they're gonna still be rotating the same direction.
And the accretion disk would be on the equivalent plane of the ecliptic now.
That's correct.
Yeah,
that's correct. And so
the ecliptic is the line between the sun and the Earth, or the line that goes between whatever planet and the Earth that almost all the planets are on, except for is it Uranus that's off the ecliptic by like a pretty big distance?
I think maybe it's Pluto.
It's one of them that's way off. Okay.
Yeah. But the basic idea is you have that like very short time frame that you need to be able to grow these planets. And so that's an important problem in current astrophysics called the meter problem.
Okay.
Because you have this dust that if you say you just have dust in the room, it can like clump with other dust via like electrostatic processes. So dust clumps together. And if you have like a big, like, a boulder-sized thing, like 100 meters across, that thing's going to start attracting things gravitationally. But how do you go from like these like dust bunnies up to like 100-meter-sized rocks?
Right.
Like how do you bridge those like 6 or 7 orders of magnitude? That's a fundamental problem in planetary formation.
That does seem interesting because you end up with things like Phobos and Deimos, which are small, like 12-kilometer wide rocks.
But they can still attract things gravitationally.
Right.
Really, like how do you go from like something that's a sand grain?
Yeah.
Because like sand grains aren't attracting other sand grains gravitationally.
Where does it start? Where does the coagulation begin?
Exactly. How do these particles coagulate? Because so you might ask like why do you have this 10 million year time limit? And it's because the dust particles, they don't feel pressure, okay? And so you have gas mixed up with dust. And so the dust doesn't feel pressure. And so it basically feels a headwind from the gas. And so that headwind acts as like friction, or like you were saying, you start losing angular momentum.
Yeah.
And so that dust starts falling into the star.
Okay.
And so the rough estimate is based on how strong the headwind is, you have about 10 million years. And otherwise, you're just going to accrete everything.
So the beginning of our solar system, there's probably somewhere in maybe 30 planets, and they are getting pushed in and out mainly because of Jupiter and Saturn.
So people do these simulations where they call it an N-body simulation.
Yeah.
So you say, okay, let's put like 1 million of these particles orbiting around, and they're going to collide and kick each other, and some of them are going to clump together. Some are actually going to get ejected from the system. And then you just see, okay, where do they end up?
Yeah.
Right? And that can kind of give us clues about like how the solar system formed. Basically, there might be like patterns between like, oh, what's the distance between the first planet and the star, and what's the distance between the second planet and the star?
Right.
Because there's these things called resonances.
Yeah.
Which, like, I mean, a famous example of a resonance was that bridge that just collapsed.
Yeah.
So they built. You could like look this up on Google. There's basically this bridge that they built it so that when the wind was blowing at like a certain rate, the whole bridge was just vibrating in resonance, and it ends up like just shaking like huge amplitudes.
Oh wow!
So this like a common feature in physics, where if you have a resonance, then you'll get kind of like new kinds of physical effects.
Okay.
So a resonance in planetary physics means when bodies are certain ratios away from other planets,
yes,
then they're going to be like incredibly stable. So this kind of theory you can use to explain like the positions of like moons of say like Jupiter. Mm-hmm. So you look at like, oh, what's the distance between?
So Io, Callisto, Europa, and Ganymede. I believe Io is the furthest one out. Like one of them is significantly further out than the rest of them, I believe.
I think Io is the closest.
Io is the closest.
It's the one that has the really strong magnetic field.
Okay.
Yeah, and which one's the furthest?
Europa is made of almost completely of ice. Ganymede is the one that's actually larger than Mercury. Is it Callisto?
Yeah, Ganymede's the big one. I'm not sure.
Jupiter is so big that its largest moon is larger than the smallest planet. In area, not in mass. Mercury is actually larger in mass than Ganymede. Here. Yeah. But yeah, I think that part is pretty cool. But like you were saying, that they're in resonance with each other, those four moons.
I think 3 of them are in resonance.
Because I'd heard that with Saturn and Jupiter that there was some kind of resonance between them.
There's all kinds of resonances between all the planets. You can at one point this theory was actually debunked, but they plotted the distance between like all the different planets and the sun, and it there was some kind of like pattern that it goes like all like the squares of like certain whole numbers, and people thought there was something to it. It ended up being like incorrect.